Number 56. A football quarterback is moving straight backward at a speed of 2 meters per second when he throws a pass to a player 18 meters straight downfield. The ball is thrown at an angle of 25 degrees relative to the ground and is caught at the same height as it is released. What is the initial velocity of the ball relative to the quarterback? All right, let's start with the question. It says, what is the initial velocity, or just for now, velocity, all right, of the ball relative to the quarterback, all right, at basically the point of release? So I have a nice little picture, right? This picture, by the way, demonstrates the velocity of the ball relative to the earth, or AKA the ground, because it's telling me that the ball is thrown at an angle of 25 degrees relative to the ground. That's what I've shown here. It has some initial velocity. The ball basically has a range, right, of 18 meters. So why don't we do this? Let's first actually just find the initial velocity of the ball relative to the earth. Now this is, you might say, relative to the earth, how do I do this? This is what you've been calculating in the prior projectile motion chapter, all right? What we can do is we can use our range formula over here on the right-hand side. So it says that the range is going to be equal to the initial velocity squared times the sine of 2 times that release angle divided by then g. So in this case, the range here is 18 meters, right? That's how far the ball was thrown. The initial velocity now is what we're looking for, multiplied by the sine of 2 times that release angle of 25 degrees, all then divided by g, which is just 9.80. Right? G, remember, is the positive. It's the absolute value of the acceleration due to gravity. So now all we have to do is solve this for VI. What I'm going to do is I'm just going to do some quick cross multiplication. And it's actually very simple. You know, this term I can bring out of the denominator and up into the numerator on the left-hand side. I can also bring this term from the numerator on the right-hand side and basically down into the denominator on the left-hand side. So I like to think about it as like a little cross, well, multiplication, right? So it's going to be 9.80 times 18, all then divided by the sine of 2 times 25. And that will equal now V, the initial velocity squared. Again, all I'm doing, if you think about it this way, if I have A over B is equal to C over D, all I'm doing, and what you're allowed to do is you're allowed to move these terms diagonally, all right, whatever term you want across that equal sign. And if you had, like, let's say another letter here, E, if B was multiplied by E, you're allowed to separate these two. Okay, you can move just the E, or just the B, or move both. All right. If these two, though, were, what happened there? Okay. If these two were just added, though, together, B and B plus E, you're not allowed to separate this E now. You cannot do that. You have to move the whole thing. All right. Anyway, just a quick little visual there. Now, this is the velocity squared, but I don't want to know the square of the velocity. I want to know just the velocity, so you got to square root both sides. Okay. And now this will help us calculate now the initial velocity. So let's just calculate that. Take out the calculator. Square root of 9.8 times 18, divided them by, make sure your calculator is in degree mode, please, not radian mode, times then the sine of 2 times 25. Close all those parentheses, and we get a value here of roughly 15.17477, blah, 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 right? I'm going to round, but when you do your calculations, just round at the end, okay? So use all exact values. So this is going to be meters per second. Now, this is the initial velocity. Now, since we're in the relative velocity chapter, this is technically the initial velocity of the ball relative to the earth. Okay? That's the frame of reference. All right? This is the ball. This is all in frame of reference relative to the earth. So what I just found here is the initial velocity, okay? I'm just going to call it now the velocity, but this is the velocity of the ball relative to the earth initially. Okay, just keep that in mind. All these velocities are going to be initial. I don't want to keep writing I because I got to add an x later. And it's going to be, you know, going to look like a whole bunch of mumbo jumbo. So anyway, okay, so that's my velocity of the ball relative to the earth. All right, now we have that in hand. Let's now go back to the problem. Okay, now, and by the way, this is the velocity, right? Also, the direction of this velocity is at 25 degrees, you know, north of east, okay? So just also keep that in mind, at 25 degrees N of E. north of east. Or you can call it 25 degrees, counterclockwise relative to the positive x-axis. It doesn't really matter. Any case, now let's start getting into the crux of the problem here. So it wants to know the initial velocity of the ball relative to the quarterback. Okay? Now, take a look at this relative velocity formula. If I want to find the relative velocity of the ball relative to the quarterback, okay, then I must know the velocity of the ball relative to the earth, let's say. Right? It all depends on what you call A, B, and C, right? So the velocity of A relative to C will equal the velocity of A relative to B plus the velocity of B relative to C. A, B, and C are just letters, right? They don't represent anything necessarily, but the relationship between them and how you must order them in the formula is very important. So I'm just simply calling my A the ball, and my C will be the quarterback. Okay, what that means is then the B in the formula, I know that might be confusing because I got like two B's there, but what are you going to do? The B here then will represent some other third entity, not the quarterback, not the ball, but what's the other third piece in this problem? Well, the earth, right? The ground or the earth. So that's going to be the B of the problem. And therefore, the velocity of then, remember, my A was the ball. I know this is probably getting confusing. You might have to rewind it 14 times because I'm even confused. But hopefully, after the 14th time, it'll make sense. So this is the velocity of the ball relative to the earth, plus then the velocity of the earth relative to the quarterback. All right, so this is kind of the formula we're looking at right now. In order to find the velocity of the ball relative to the quarterback, I need to know the velocity of the ball relative to the earth, and I need to know then the velocity of the earth relative to the quarterback. All right, so a couple things to keep in mind. Whenever you add velocities together, you can only add x and y components. All right, you cannot add x and y together. You kind of have to separate them. What I mean by that is this. In order for me to find the overall velocity of the ball relative to the quarterback, I have to know two things, or I have to be able to sum two things. If it is a two-dimensional problem, which it is, I have to take the velocity of the ball relative to the quarterback in, let's say, the x direction. And that should then equal the velocity of the ball relative to the earth in the x direction, plus the velocity of the earth relative to the quarterback in the x direction. Okay? Then, I must also do the same thing for the y components. In other words, the velocity of the ball relative to the quarterback in the y direction. That looks like a 4. In the y direction will equal the velocity of the ball relative to the earth in the y direction, plus then the velocity of the earth relative to the quarterback in the y direction. All right? So I have to look at this now in two pieces, all right? Now, let's take a look at the x part first, okay? So in order to find the velocity of the ball relative to the quarterback in the x direction, I must know the velocity of the ball relative to the quarterback in the x direction. Now, I don't know what that is at the moment. All I know is that the overall resultant velocity of the ball relative to the earth, I could put it like a little r down there, all right, is going to be equal to 15.2 meters per second. But it's at 25 degrees north of east, right? And wait a minute, if you know the resultant vector and you know the degree, you can find then the x component, right? So, in other words, let's just look at this coordinate plane. I have this velocity vector. This velocity vector now is going to be 15.2 meters per second, but I'm going to leave out the units, and this is going to be 25 degrees. This, in red right now, is going to be the velocity of the ball relative to the earth resultant, right? That's the resultant vector, okay? So now what I want to do, I'm going to leave out the r though for now. Now what I want to do is I want to find just the x component of this. So how do we do that? How do we find then the velocity of the ball relative to the earth in the x direction? Well, it's simple, right? I mean, we could just start using sine, cosine, tangent, right? All our formulas. So I noticed that this is kind of, this side in brown here is going to be adjacent to the 25 degrees, and that's basically the hypotenuse, right? You see a little triangle there. So I'm going to use a cosine. Okay, so I'm going to do cosine of the angle is going to be equal to the adjacent side over the hypotenuse. The cosine of then 25 should be equal to now the adjacent side, which is going to be my unknown, which is the velocity of the ball relative to the Earth in the x direction, divided then by the hypotenuse, which is the 15.2. Okay? Oh, look, I can solve this now, right? You got only one unknown. So therefore, the velocity of the ball relative to the Earth in the x direction is going to be simply 15.2 multiplied by cosine of... Now, 1 second. When you do this calculation, use the exact value you found from before, please. So you have to go back in the memory of the calculator, grab the 15.17477, blah, 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 and then multiply that by cosine of 25. All right? So in the beginning here, I'm not really too keen on that because these problems are hard enough. So I try to I round heavily, and I'm trying to just get you the main gist of how to approach physics. Later on in the series, I do this much more specifically. But anyway, so this is going to be 13.753, blah, blah, blah. So I'm just going to round 753. No sig figs here. But that's going to be the velocity now of the ball relative to the Earth in the x direction. Okay, that is this piece right now. Okay, so why don't we take this and just move it on up here for now. All right. Now, while we're at it, since we have this picture already, all right, why don't we find the y component now? All right, why don't we find that y part? So I'll do this part in black. So now the y part is just going to be finishing out this part of the triangle, right? This will be the velocity of the ball relative to the Earth in the y direction. And this is all simply going to be, it's going to be sine now, okay? So it's just going to be a sine calculation. So it's sine of theta will equal the opposite side of the angle divided by the hypotenuse. The sine of that angle, 25 degrees, should equal that opposite side, which is the velocity of the ball relative to the Earth in the y direction. All divided then by the hypotenuse of 15.2. Use that exact value, though, in your calculation. Okay, so 15.17, blah, blah, blah. Multiplied then by the sine now of 25. 6.143 or so, right? So we're going to get now and I'm just going to write it up at the top, that the velocity of the ball relative to the Earth in the x direction will be equal to 6.413. These are all meters per second. I'm leaving out the units because it's just going to get really a little crazy, okay? So that takes care of that, all right? Now, what we need to do is, basically we found this piece, I might have circled this, I'm sorry if I did, but we found this piece, and we found this piece. Okay, so we got each of these two parts independently, and remember, we're solving for this piece overall, so in order for me to find this, I probably should know this first, okay, and I should know this next. All right, now, let's erase this little diagram, we really don't need it anymore. Now we're going to focus on the second part, okay? So this is talking about now the velocity of the Earth relative to the quarterback. Now, I know that sounds strange, and by the way, in the x direction. I know that sounds strange. Now, you have to remember this, that if you know the velocity, and this is always true, of I'll use any two letters here. If you know the velocity of x relative to y, then you will also know the velocity of y relative to x. You just got to put a little negative sign in front of it. Okay? That's all you got to do. Right? If you're moving at 2 meters per second relative to the wind, positive 2 meters per second relative to the wind, then the wind is moving negative 2 meters per second relative to you. Okay? So that's the idea here. So what might be easier now is instead of looking at this as the velocity of the Earth relative to the quarterback, it's like, wait, what? The Earth? It's moving, right? Of course it's moving, but wait, relative to that's a little confusing. It's always easier to, instead of finding the velocity of the Earth, well, usually easier, instead of finding the velocity of the Earth relative to the quarterback, it's usually easier to find the velocity of the quarterback relative to the Earth. Because everything we kind of study here, the motion is relative to the Earth, right? When you're looking at the ground doesn't look to be moving to you. It's the ball that's moving, right? Or the quarterback that's going to be moving backwards, right? But it's moving backwards. He or she is moving backwards relative to the Earth. Okay, so that's why it's always nice to put the Earth at the end. Now, once I do that, though, I have to negate it, right? I have to make this minus now. So in other words, I have my new equation. Like, how many new equations are there going to be? This should be it. BEX, okay. and this is all in the x direction, and the same thing I'm going to do over here. All right, the velocity of the ball relative to the quarterback in the y direction should be equal to the velocity of the ball relative to the earth in the y direction minus then the velocity of the quarterback relative to the earth in the y direction. All right, just to make a little more space here, I'm going to erase this now and move those two on up. Okay, and I realize I could probably also, that box might move. Ah, there we go. All right, I'm going to get rid of this for now, okay, because we really don't need that either. All right, so now let's think about this. The velocity of the quarterback relative to the earth in the x direction. What did they tell us? Well, it said this. The football quarterback is moving straight backward at a speed of 2 meters per second. Wait a minute. 2 meters per second relative to what? By gosh, by golly, they didn't give it to me. Well, if they don't give it to you, it's fair to assume that this velocity is going to be relative to the earth, right? It's moving, he or she is moving backward at 2 meters per second relative to the earth. In other words, what they gave us here is they gave us the velocity of the quarterback relative to the earth. Okay? That's what they gave us. Now just consider what's going on in the picture of the problem. Right here at the origin is the quarterback, okay? You can think about it as a quarterback or the ball. It really doesn't make a difference, all right? But this is the quarterback. So the quarterback throws the ball at 25 degrees, relative to the horizontal with an initial velocity of 15.2 roughly meters per second relative to the earth. At the same time, the quarterback is also moving backward relative to the earth. So the velocity here of the quarterback relative to the earth is going to be, in this picture, it's 2 meters per second, right? But you got to be careful now. Once you start taking this value out of this picture, okay, and you start plugging it into formulas, it's got to be a negative value. Why? Because it's pointing in the negative x direction, okay? So this might get confusing, but it's going to be a double negative. So let's take a look. Ready? So velocity of the ball relative to the quarterback in the x direction should be equal to the velocity of the ball relative to the earth in the x direction. That's what we found up here. So we're going to take our 13.753. Minus now the velocity of the quarterback relative to the earth in the x direction. So the velocity of the quarterback relative to the earth in the x direction is 2 meters per second. They're moving backwards and to the left. Therefore, it's a negative value. When you plug that in, it has to be negative. This negative was independent. The reason why this negative showed up is for what I explained before, because I kind of switched those two terms down there. Okay, so this is going to be 2. Cool. And so now we can solve this, right? The velocity of the quarterback the velocity of the ball relative to the quarterback in the x direction. My God, this is confusing. This is 15.753, right? That's going to be meters per second. Okay, we finally got that part. Let's put that a box around it. Now let's do the same thing for the second piece. Now watch how easy this is. The velocity of the ball relative to the quarterback in the y direction should be equal to then the velocity of the ball relative to the earth in the y direction. We found that, 6.413. If you're bashing your head against the wall at the moment, I understand. So am I. Ow. No, don't do that. Don't do that. Don't do it. Just kidding. That was my hand on the table. I didn't really bash my head. Anyway, what's the velocity of the quarterback relative to the earth in the y direction? Well, look at it. The quarterback is moving backward, right? Is this quarterback moving in the y direction at all? Is he or she moving up or down at all? Is there some vertical component? No. So guess what? Big ol' fat 0. Okay? So the velocity of the ball relative to the quarterback in the y direction will be 6.413. Okay? And notice that these are both positive values. Now, finally, guess what these are? These are really just x and y components. That's all it is. I know all these subscripts are confusing, and it's like relative velocity, it's all confusing. All the velocities we spoke about in the past, they're all relative. By the way, there is no such thing as an absolute velocity. Okay? They're all relative. In the past, you might say, well, we didn't even talk about it, so what do you mean? The assumptions were that all those velocities were relative basically to the earth. Okay? We're just stating it explicitly now. So what I'm going to do, take my x component here. I'm going to put that in red now. That x component is positive, and it has a value of 15.753 meters per second. Okay? Then I'm going to take my y component that has a value of, this is not totally to scale. Okay, but this has a value of 6.413. And now, to find the initial velocity, which all these are components of the initial velocity of the ball, the overall initial velocity of the ball relative to the quarterback. Guess what? That's now this resultant. Okay? That's the resultant now. R. All right? Finally, we can find it. Okay. So now what I'm going to do, because there's not really a lot of room at all, I'm going to erase all this beautiful stuff. Okay? You should have all the information saved on your calculator now. And I'm just going to start to plug in some stuff. All right? Hopefully you're having a good semester. Or at least you were before you got to this problem, right? I was having a good day before I got to this problem. But hey, what are you going to do? Right. So now I got to find the R. Okay, so we're going to use, we can use Pythagorean's theorem. A squared plus b squared is equal to c squared because we're talking about a right triangle here. Here's the right angle. And a squared, it's 15.753 squared is going to be plus 6.413. Now, when you do these calculations, please use the exact values. All right. So to find the R, I have to now square root both sides. So we get that the resultant vector here, which is the velocity of the ball relative to the quarterback, should be equal to now square root of, go back and find those exact values. Well, I didn't add the 2 to it when I did it in my head. That's part of the problem here. So 13.753 blah, 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 plus the 2, okay, square it, and then add to that the 6.4131 blah, 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 square it. We get a value here now of 17.008, right? Now we can start rounding though, when we get our answer. So this is 17.0. This will be meters per second. Now this resultant velocity was the initial velocity. So we can just call this the velocity of now the ball relative to the quarterback, okay? No x and y, this is the overall resultant velocity. Now, what you can also do when, solving for velocity, you can also give the direction. And direction, we're talking about then the angle. So the angle in here, all you got to do is a tangent calculation. So tangent of that, you could do sine, you could do, you could do this, but maybe you made a mistake here, silly calculation mistake, right? And, you might not want to use that. Now, you might have also made a mistake here too. Well, you can't avoid that. But, this is just another, how do I say? This calculation was further downstream, so to speak, or came after these calculations. So, there's a higher likelihood that there's an error in this rather than in these two. Although, anyway, I'm overthinking this. Adjacent over opposite. What? Opposite, I'm not overthinking it. Opposite over adjacent. So I'm just trying to confuse you at this point. Tangent now of that angle will be equal to the opposite side of the 6.413 divided by the 15.753. Use the exact answers when you do this. To find then that inverse tangent, right, to find then the theta, you have to take the inverse tangent of both sides. Okay. And that basically cancels the tangent on the right. You get your theta. And now just go in and calculate. So inverse tangent of, grab that exact answer, the 6.4 blah, 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 and then divide it now by the 15 blah, 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 blah. Okay. I got to add 2 to it. Okay, so you get 22.15, right? And I got to round to 3 sig figs here, so it should be 22.2. And that's in degrees. And the degrees are now relative, right? You could say 22 degrees north of east. You could say, I'm also assuming that this problem is moving to the right. You can say counter clockwise from positive x-axis. It doesn't really make a difference, but you can say from the positive horizontal, whatever you want to call it. And there you go. Those are the two values. So it's 17 meters per second at 22.2 degrees relative counterclockwise from the positive x-axis. Wow. Thanks for tuning in. I hope you enjoyed this one as much as I did. And if you did, even if you didn't, like and subscribe. Tell your friends. All right? Tell your parents, tell your classmates, tell your uncles and cousins, anybody who's interested in physics. And even if they're not, tell them. Tell them, just talk about it. The mailman, go for it. Thank you.